Hello, everybody. Hey, this is going to be a lecture primarily on torque and angular momentum. But before we get there, we need to take care of a few little math details, which can definitely be kind of confusing. And those two math things are when you multiply a vector times a vector. Now, we've already done this in terms of work. And we're also going to do it in terms of torque. Now, if we take a look at work, which I've gotten on the board, so work is equal to force times distance, okay? And that is as long as they're going in the same direction. If they're not going in the same direction, then it's going to be F times D times the cosine of theta. Now, if we have it in vector notation, which as you may remember would be I and J or IJK, then it would be the force vector dot displacement vector, okay? And what we've got up here, for example, is if we had 3I, 4J, which would be, let's say, in meters, and 2I, 1J in newtons. So if we wanted to calculate what the work was, we could multiply these two vectors. And really what we'd have to do here is just FOIL this, right? And so we're going to say 6I squared. So first, and then we're going to have 3IJ and 8IJ. And finally, we're going to have 4J squared, okay? And as we can clearly see, that this is equal to 6, this is equal to 0, this is equal to 0, and this is equal to 4. Therefore, our answer is 10. Our answer is 10. And if, in fact, we were dealing with work, our units would be joules. So the obvious question there is, how come 3IJ is equal to 0 and 8IJ is equal to 0? And the answer is, if we kind of go back and look at that, that cosine, that FD cosine theta. So remember that these vectors are essentially going in the X and Y direction. So if we have I times I, they're in the same direction, right? So we're going to take the cosine of 0 degrees, and the cosine of 0 degrees is 1. So we're basically saying 6 times 1, which is 6. But when we get to the IJ, now we are at right angles, and now it's an angle of 90 degrees. And we know that the cosine of 90 degrees is going to be 0. So 3 times 0 is 0, 8 times 0 is 0, 4 times 1, because that is essentially in the same direction, the angle between those J's is 0. And so we were going to have an answer of 10. And in this case, since we've got meters and newtons, we're going to have 10 joules. Now, remember that energy is a scalar, okay? So it has no direction. So when we go to do, or this is also called a dot product or a scalar product. So you probably haven't been paying attention, but I have specifically, when we talk about work, talked about putting a dot there as opposed to an X or a cross, okay? Now, an example of a cross product might be torque, okay? Now, torque, it would be a vector, and that would be a force times the radius, force times the radius as long as it's perpendicular, which would equal to force times radius times the sine of the angle. That's if it was not perpendicular. And if we have two vectors, we can say that R cross F would be equal to the torque. Now, this is called a cross product, also known as a vector product. So our answer to a cross product is a vector, which means it's going to have direction. Our answer to our scalar product is just a scalar, so it does not have direction, which makes the cross product a little trickier than it is with a scalar product. So if we end up doing this, and I'm going to slow this down here, and we're going to erase some things and do another example. So hold on one second here. All right, so I'm back here, and now I've got some stuff up here for us to sort of process here. So if we have a vector, the answer to vector C is equal to vector A cross vector B. This would be like torque is equal to radius times force, right? The vectors. Now the magnitude of this would just be the absolute value of A times the absolute value of B times the sine theta, which is what we just kind of covered here. But where there are certain properties, you guys, there are certain properties of a cross product, and you'll find this stuff on page 312. So I'm just going to kind of briefly go over this. But if vector A cross B is equal to the negative of B cross A, so if you switch the order, they're not equal. Okay, if they switch the order, it's not equal, but they become the negative of each other. If A and B are parallel, which means either going 0 degrees or 180, then they are going to be equal to 0 because the sine of 0 or the sine of 180 is equal to 0. And the property 3 is if they are perpendicular. If they're perpendicular, and then they're at 90 degrees, and then the sine of 90 degrees is 1. So then it just becomes the absolute value of A times the absolute value of B. So also, if we have A cross the quantity of vector B plus C, then we can just distribute that vector. So A cross B plus A cross C would be equal to A cross the quantity of vector B plus C. And finally, this is going to kind of come here at the end. If we take the derivative of A cross B, then we can take the derivative of A cross B plus the derivative of A cross derivative of B. All right, so this can be a little bit confusing. So part of this, you want to just sort of struggle through this. And if you're having a little bit of trouble, you can kind of go back and read on page 312, 303, 13, 314, and our question of the day for 428 is going to be similar to what I'm about to do. So then you can kind of follow this, and there is also going to be another example in the book on page 313 with different numbers. It's essentially the same thing. Okay, so if we have A cross B, okay, then we can set this up as a 3x2 matrices. Okay, so here we have 3i, 4j, 1k, so that would be ax, ay, az, and then we're going to have 2, 1, negative 2, ij, and k, so that would be our bx, by, bz. So if we have this sort of matrices, we can break that down. We can break that down into the matrices of y and z, which would give us the I direction. Z and X would give us the J direction, and X and Y, which would give us the K direction. All right. So again, if you're really having to do this a lot, right, there is a program in most calculators, most scientific advanced calculators, like the TI 90, the 94, the 93, or whatever one you might have. There's going to be a program for putting in matrices. And you guys might already be aware of that, and you can just plug this stuff in. But I think it is important for you guys to just think about the actual process in your head once or twice so that you know in your head that mathematically, logically, it makes sense. And that's what we're going to try to do. That's what we're going to try to do right here. Okay, so essentially once we have these numbers set set in here. So let's just talk about this being 3, 4, 1, and 2, 1, negative 2. All right, so if we want the I direction, essentially we're covering up this and we're saying 4, 1, 1, negative 2. And now we're going to do the actual cross. So we're going to say 4 times negative 2 minus 1 times 1. 4 times negative 2 minus 1 times 1. All right, so this is going to be, did I set that right? So 4, 1, 1, negative 2. So that's going to be negative 8 minus a positive 1, which would give us negative 9i. So the first part in the I direction, or think about it in the X direction, our magnitude is going to be 9, and it's going to be going in the negative I direction. All right, so now we're going to do the same thing here, but now we're covering up this 4 and 1, or the J column, and we start with Z, and then we're going to cross it with X. So we're going to have 1, negative 2, and 3, 2. And so now we're going to do the cross. So we're going to have 1 times 2 minus negative 2 times 3, which is going to be 2 minus a negative 6. Minus 2 minus a negative 6, which this negative and negative is going to give us a plus, and now we're going to have 8. But that direction is J. We're going to do this last column, which now we kind of cover up the Z column, and we're going to have 3, 4 cross 2, 1. 3, 4 cross 2, 1. So this is going to be 3 minus 8. 3 minus 8 is going to be negative 5, and that's going to be the K direction. Okay, so vector C in this case, okay, and when we do A cross B, would equal this these components to the vector. So we'd go minus 9i, positive 8j, negative 5k, and we'd end up with a 3-dimensional vector. Okay, so if this was in fact meters and newtons, okay, then we would have the units here, and this vector C would in fact be a value for a torque. Okay, but it doesn't quite matter whatever those units might be. So obviously there's going to be an application to physics here, and there are many applications when you get further into electromagnetism, etc. And also, curiously, in computer science, there is a lot of application for these cross products, which will kind of be in your future. Now, you guys, we're going to do a little more practical example here. And let me sort of grab something here. 1 second. Okay, so I'm back. So what does this mean? What does this mean? Well, it means that if we put in a 3-dimensional sort of thing, if here is our I or our X, right? So we're going to go negative 9, and then we're going to go up 8, and then we're going to go negative 5, okay? So this is going to be negative 8 plus 9, negative 5, right? So we got to think of this in 3 dimensions. So now that would be our resultant vector. That would be our resultant vector. Okay, so this seems pretty complicated. And for the most part, you guys, it's pretty easy to kind of make this a lot easier, right? So if we have, let's say, a wheel like this, right? Then if we twist it, right? I just applied a torque to this. So now my force was in this direction, and my radius was in this direction. So we essentially, as soon as we have a force and a distance, or a distance and a force, it automatically turns into a plane. So for example, if the screen that you're looking at is our plane, right? And we have a radius vector, right? So it could go X, and then it could go Y, and then it could go Z, right? So it's not in the plane. And we take another one, and let's say we're going to go X, Y, and Z, right? So now that is no longer in that X and Y direction. But if we pick it up, then we can see and align it. There's going to be a plane. There's going to be a plane between that radius and that force. So it doesn't really matter unless we have a specific plane that is imposed on us. We can essentially just change it around so that we end up with, let's see, a plane like that. Okay, so for the most part, we're only going to have this two-dimensional sort of thing. So now let's take a look at this. If we got rid of, you guys, if we got rid of this K, essentially it becomes 0K, then what's going to happen? You guys, what's going to happen to this? This whole calculation is going to go away, and this whole calculation is going to go away, and our answer would just be -5. Our answer would just be -5. Okay, so we're going to go back to our original. Okay, we're going to go back to our original, and we can see here that we have a 3-4 and a 2-1. So the same sorts of things, except now we're getting rid of the K. And now we're going to end up with, when we do this absolute value, right? So we're going to still have this 6i squared. This 6i squared is going to be 0. Okay, and now we're going to get 3, and now we're going to get 8, and now we're going to get 0. So now when we add these together, okay, we're going to have different possibilities. We could say -3 plus 8, which is +5. We could get 3 plus -8, which is -5, and then we could get 11, okay, and we could get -11. So those are possible things. And we could see from the last one that our answer was -5. Okay. Now that is why this cross product makes it a little trickier than the dot product, because the dot product is just going to be whatever that magnitude is. We don't have to worry about direction. Okay. So also, it's a little bit curious. It's a little bit curious to think about the direction, right? But if we make this, for example, our answer here. So we're going to say if this is our x, let's kind of do it this way. Okay, if we're going to make this our x direction and this our y direction, like so, okay, and now we're going to say -1, 2, 3, 4, 5, 6, 7, 8, and we're going to go -9, +8, okay, then our resultant is going to be this. But, if we go to our original, 3, 4, if we go to our original 1, 2, 3, 1, 2, 3, 4, we're going to have, this would be essentially vector A. That would be vector A. So notice it's in the first quadrant. So we're going to take a look at our second vector, which is going to be 2, 1, which is going to be 1, 2, 1. And this is going to be vector B. Okay. Now, if we look at this, okay, and we know the answer, we know this answer is -5. Okay. And what we can do is say what's called the right-hand rule. Okay. So if we take our first vector, okay, and we point our fingers in the in the direction of our first vector, which is this way, and then curl it towards our other vector, the direction of our thumb is going to be the direction of that vector, okay? So now if I do this, okay, and I take my vector A, curl it towards vector B, and now my thumb would be sticking out the bottom. So that is going to be the direction of that vector. And it happens to have a magnitude of 5. Now we can do some quick calculations. Okay, if we now take this 3, 4 and this 1, 2. Okay, now we know this 3, 4 triangle is going to have an angle of 53 degrees. So if we have this 1 and 2, that happens to turn out is going to have an angle of about 26.6. We're going to call it 26.5. So the magnitude of this first vector, it's a 3, 4, 5 triangle, right? A squared plus B squared equals C squared. And the magnitude of our second vector is going to be 2 squared plus 1 squared square root. So that's going to be 5 times the square root of 5. And now the angle between these two, 53 minus 26.5, is essentially 26.5. And if we take this and do the sine of 26.5, okay, then we're going to, let's see this, we're going to say 11.2, okay, and we're going to multiply that by, and we're going to get 4.9886, right? So that is going to give us, that's going to give us the same value that we got here, which was which was 5, right? That gives us the magnitude. It's just the direction that we have. And so we know from doing that cross product that that direction would be in that negative direction. Okay, so how does that relate? How does that relate to vectors here? And essentially what we have here is something that is rotating, in order to get it to rotate from 0, we need a torque, okay? And once we have that torque, now it is spinning. And that's going to lead us, because that's going to lead us into the next section, which is going to be both torque and angular momentum. So I'm going to erase some stuff and rewrite it, and then come back to you in a second. All right, so we're now going to look at, going back to review, F, or force, is equal to mass times acceleration. If we go back to linear momentum, P is equal to mass times velocity. So that's kind of going back to that momentum chapter, linear momentum. Remember also that impulse was equal to force times time. So if we apply a force to an object for a certain period of time, then we're going to change the velocity, okay? Now, if we divide both sides by t, okay, then we can say that the force is equal to mass times the change in velocity over the change in time, okay, which is equal to the change in momentum over the change in time, okay? So this mv and the change is going to be change in momentum, okay? Now the change in momentum, if we want to turn that into a derivative, that is going to be dp dt, and that is going to equal to the force. Now, if we want to get a little more elaborate, we got to remember that it's the sum of all those forces that are going to be operating. Okay, so now if we go back to think about what we did here in a little bit ago, okay, that R cross F, and that F is just the sum of all the forces, right? We could have 20 forces. We could have 20 forces there, but when we added them all together, it would be a single vector that would have, in 2 dimensions, would just be have an I and a J, just like the example that we just did. okay? So we're going to essentially get ij and ij, and the sum is equal to the torque. Now, by combining this stuff over here, we can see that we get, this would be r cross change in momentum divided by the change in time, because that is force, okay? Force is change in momentum divided by the change in time. So if we then go back and look at this property number 5, which is talking about the derivative of a cross product being the derivative of one vector times the other vector plus the first vector times the derivative of the second vector, we're going to end up with this. And if we have this, then we can kind of come down to this, okay? So remember that torque is our angular analogy to force. Torque is our angular analogy to force. So in the same way that we had change in momentum over the change in time from a linear force, now we can see here that this, the analogy of the R and P is going to give us angular momentum. Okay, so we're going to define this, okay? We're going to define and say that angular momentum, okay, is going to be equal to the cross product between R or radius times the momentum, all right? So this is angular okay, so this is our definition of angular momentum. So this is like our P, but we've translated it into an angular sort of sense. And just like with linear momentum, there is also going to be conservation of angular momentum, which I will talk about here in a minute. So essentially, if we define angular momentum there, kind of from extracting this here, this right here is now what we're going to define momentum in. The torque is equal to the change in angular momentum, with respect to time. Okay, so we are now, I want to show you an example. I need to find. All right, so I found my my wheel here. So if I wanted to impart an angular momentum to this wheel like I did, so what I'm going to do is I'm going to apply a force and radius, and now since this thing is spinning, okay, it's going to have momentum. And if I now apply a torque to that, now just by letting go, there is going to be a torque due to gravity. And because there's a torque, now it is going to be moving. It's going to be moving, but not in the direction of one or the other, but perpendicular. Okay, so the direction of the vector between radius and force, or the change in momentum, the change in angular momentum with respect to time, is going to give us a resultant of the object moving in the direction of k, or the z direction. So it is going to precess. It is going to move slowly as we move this. And if I try to do it in the opposite direction, okay, we can see that it is going to precess in the opposite direction. Okay, did you ever wonder why, when you were riding a bike, okay, so think of the bike and you're going around and you wanted to make, let's say, a right-hand turn, and you don't turn the steering wheel, okay? You don't change the handlebars, right? All you do is lean into it and when you lean into it like this, you're essentially applying a torque, and the direction that it's going to now precess is going to be to the right. Okay, so just by leaning, you're taking advantage of this concept here of torque being the change in momentum over time. But the change in momentum is not going to give you something in an XY plane, but it's going to give you something in the Z direction. And again, if you lean the other way, then you are going to turn the other way. So it's going to precess in the opposite direction. So again, you guys, we will elaborate on this, but for the beginning, we need to calculate, just do a little bit of this cross product, both in 3 dimensions, IJK, which is what the question of the day is for 428. And most of the time after that, we're just going to have 2 dimensions. And the resulting value is either going to be in the positive z or the negative z direction, according to the right-hand rule, which we will probably elaborate. So one thing that I'm thinking of that I forgot to mention, when we have a three-dimensional vector, then if we want to know the magnitude, then we're going to use Pythagorean theorem. So remember that a squared plus b squared is equal to c squared, right? So Pythagorean theorem. But the Pythagorean theorem works in 3 dimensions as well. So if we go a squared plus b squared plus c squared, and that would equal to d squared. So this would be like x and y, or I and j, and this would be like x, y, and z, or I, j, and k. And so if we just want the magnitude, just the c and the d, then we're going to take the square root of all that. So Pythagorean theorem works not just in 2 dimensions, but in 3 dimensions right there. And you're going to need that for the question of the day. All right, until next time, we will see you later.